Hi everyone, we are the PIDE Avocet team from the FIERCE Avocet pod, and we worked on the Human Connectome Project dataset. We wanted to address the question and see if we could use the neural activity, in our case, the blood oxygen level dependent signals, to predict the subject performance on the 2-back and the 0-back tasks, working memory task. Our hypothesis was that individuals who display a higher bold activation will perform better on the 2-back task, and we should be able to decode this information and predict the outcome. We had data from 339 subjects, and we performed stratified k-fold and oversampled the incorrect responses before classifying. And we used the support vector machine classification between the correct and the incorrect 2-back working memory task events.
So the first step we did was we collected all the data from all the different subjects and made it into one frame that contained all the features, the bold activation data features and the performance. And then we subtracted the average 0-back from all the 2-back activation so that it wasn't interfering with our signal. So then the next steps, we're doing a k-fold, and we made 3 folds in the data. Then we did oversampling using SMOTE that David will talk about in a bit. And then for our feature selection, we used SelectKBest to determine the best parcellations to use in our SVM classification that we used at the end.
So SMOTE is synthetic minority oversampling technique. And the reason to perform oversampling is because you see in subject 1, there are 3 incorrect responses versus 37 correct responses. So what SMOTE does is that it tries to make some synthetic data and place that synthetic data in the location where it thinks it should be. So in the incorrect responses, trying to place them close together, but not in exactly the right same spot. This allows us to increase the incorrect to correct ratio to 1-to-1, and then that's better for SVM fitting. Before sending all the data into the SVM, we also did univariate feature selection using ANOVA and determined that only about 10% of the total parcellations gave the best accuracy score on SVM. And then using this feature selection, we were able to determine univariate scores for each parcellation and SVM weights before and after selection in order to choose the best parcellations to send into SVM.
So here we see the results of the weighted SVM, so the top 36 features. And on the most left-hand side, you can see the value of these weights. And in the middle column, you can see the names of the brain regions. And on the right-hand side of that, you can see the parcel numbers. And so what we did is we want to give you a nice visualization. So what you can see on the right-hand side is the left and right-hand side of the brain. And what you're seeing is the Glasser atlas overlaid onto inflated brain. And specifically the white clusters represent the weights of our 36 parcellations. And so our hypothesis was that we'd see activation differences in cingulate, frontal regions, and parietal regions, and that's exactly what we saw. So some of these weights are associated with those regions, but also we saw significant weights attributed to the visual and somatomotor regions, which makes sense because these tasks also utilize these brain regions as well.
So as you saw in the previous screen, the SVM did not do better than chance. So running it with SMOTE, you get an SVM accuracy that's around 55%, plus or minus 0.01. And this leads to a less, in a one-sided t-test, an insignificant finding. Basically, it doesn't do better than choosing a random sample from the data set. This makes sense. Total subjects across the data set chose correctly on the two-back score 81.4% of the time. So randomly choosing a correct score is a p of 0.814. We compared SVM fitting methods and showed that under different SVM kernels, polyradial linear, and then different oversampling and undersampling techniques, that it was pretty similar across for accuracy. And one way that we could improve this in the future would be to use a nonlinear method, unlike SVM, or actually taking the subject responses during the events and breaking them up between tasks that are associated with remembering an image that someone saw 2 images ago, or words that someone saw 2 images ago, and scoring those independently to more normalize the data.
So we just want to thank everyone. This is a big group effort, great team. We wanted to give a special thanks to our mentor, Patrick McClure, and our TA, Alex Attinger, and the rest of the pod, Elliot, Michael, Olivier, Scott, and Yuan. It was a pleasure to meet everyone, and it was a great time learning.
Thank you.
Thanks, everyone.
Thank you.